Hey, welcome to class again. We're going to be talking about the atmosphere. Remember last time we talked about the geosphere, and we're going to be talking about all of these: atmosphere, geosphere, hydrosphere, and know that they all interact. Some of the things that we're going to be hitting today is the composition. What is the atmosphere made up of? What are those layers? It's so much more than just what we skimmed over when we were talking about the geosphere, and we kind of mentioned the atmosphere a little bit, that it's a mixture of gases, but it's so much more. It's got layers, and each of those layers have properties, so we'll name them and talk about them, and then we'll carry on to talking about energy transfer, radiation, conduction, convection, and then we'll hit that buzzword greenhouse effect and really talk about what that is. We did this, remember we did this warm up before. The planes, why do they fly 10 kilometers above the ground? Well, to get above the weather, that's right, above harsh winds and things like that. And no higher than that, because then you wouldn't have the oxygen. Like I said, we're going to talk about the composition of the Earth's atmosphere, what it's made up of, each of the layers of the atmosphere. Just like we did with geosphere, we talked about layers of the geosphere. We're going to be talking about layers of the atmosphere. And then conduction, convection, and radiation. And then also we'll talk about the greenhouse effect. So let's go ahead and dive in and get started. I'm excited. Okay, get this down in your notes. The atmosphere is a mixture of gases that surrounds the planet, such as Earth. So other planets do have their own atmosphere, and this is a mixture of gases. So what are those gases? They are nitrogen, oxygen, carbon dioxide, and then there's others such as argon, which is a trace element that's in the air. And a lot of these are, well, these are all important for life as we know it here on Earth. If not for nitrogen, the plants wouldn't have the nutrients that they need, because nitrogen is one of those things that plants can't get directly from the air. It has to be fixed into a form that they can use. They need a go-between, like for instance, bacteria. And we'll talk a little bit more about that in a second. And oxygen, well, that you can get directly from the air. We take that for granted, don't we? Just to get that oxygen. But what did I breathe out? Carbon dioxide, that's right. So a lot of these gases interact, go through a cycle, and become part of all of life. So you can see how Earth is really integrated: the atmosphere, and the geosphere, and the hydrosphere. Gases can be added to and removed from the atmosphere through living things. So I said I was going to get back to that. Nitrogen, for instance. Nitrogen is not usually in a form plants can have just from the atmosphere. So when it mingles with the or gets to the level where dirt can absorb it, it doesn't do good for the plants unless there's bacteria there that can fix that nitrogen to a form for the plants to use. And then that symbiotic relationship between the plant roots and the bacteria work to benefit both of them. So that's mutualistic. And then that same nitrogen can denitrify it by re-releasing it into the form of nitrogen that goes up into the air. Oxygen's not the same way. Oxygen, we breathe in oxygen, breathe out carbon dioxide. Well, plants are the reverse of that. They breathe in carbon dioxide and breathe out oxygen. So I got this nice relationship with them. And then argon gas, well, that's inert, so it's part of the mixture. By the way, let me talk a little bit about mixtures. Mixtures are not chemically combined together. So these things, gases dissolved in other gases, kind of like your soda. You shake it up, that gas comes out of it. It was always there. It wasn't chemically combined, it was always there, and it just comes out of solution. These gases are all mixed together. Other things that can introduce more stuff into the air is things like volcanic eruptions that add more gases, vehicles that add more gases, all leading up to the greenhouse effect, by the way. And the atmosphere also insulates the Earth's surface. So we'll talk about how that ties into the greenhouse effect. But as the sun's rays come striking down, it can block some of the sunlight. All the clouds and all these gases can block some of the sunlight. So if you have a volcanic eruption, it might lead to cooling, Earth cooling by a couple of degrees. Because it's blocking out sunlight. But on the flip side, if the sun's light can penetrate all the smoky ash that was being produced, then it could trap the sunlight, keeping it from bouncing back out into space and cause global warming. This insulation slows the rate in which Earth's surface loses heat and keeps the Earth's temperature at which living things can survive. When the atmosphere is in check, it's not too many greenhouse gases going out, too many volcanic ash going out, then it has a way of self-regulating and being good for us that are the living. Nitrogen makes up, so let's talk about the individual components of the atmosphere, these gases. Nitrogen makes up 78% of the Earth's atmosphere and enters the atmosphere when volcanoes erupt and when dead plants and animals decay, because they've taken in that nitrogen, and now when they die, they're releasing that nitrogen. So you can see most of the Earth's atmosphere is actually nitrogen. Oxygen is the second most abundant gas in the atmosphere and is primarily produced by plants. In addition to gases, the atmosphere contains many types of tiny little solid particles or atmospheric dust. This dust actually helps form a little nucleus for water molecules to attach to and rain down when they become heavy enough. And speaking of which, water vapor is considered one of those gases that makes up the atmosphere. In addition, nitrogen and oxygen, there's other gases such as argon, which is a trace element because it's not that abundant, carbon dioxide, which we've mentioned already, and methane. Methane, that can come from belching or farting. There's actually this big deal about all the farting the cows are doing and methane that's coming from them, and so vegetarians are like, hey, quit making so much meat and so much methane. And like I mentioned earlier, water vapor makes up the rest of the atmosphere. So here's a little diagram of that. You can see nitrogen is the most abundant, followed by oxygen, and then all the rest fits in that one little 1% right there, right over there. Okay, so let's talk about some properties of the atmosphere. You've got air pressure. Earth's atmosphere is pulled toward Earth's surface by gravity. As a result, we have an atmosphere. The atmosphere is denser near the Earth's surface. That's kind of like the geosphere, where it's, the rock layers are denser as you go toward the core. It's kind of a common theme there. But also take note that because our planet is the size that it is, we're able to have an atmosphere. Mars is a little bit smaller than Earth, so it loses its atmosphere more easily. And planets that are even smaller don't have an atmosphere. Bigger planets trap even more gases. So the size of the planet actually has a lot to do with whether it can have gases or whether those gases escape. Almost the entire mass of Earth's atmospheric gas is located within 30 kilometers of its surface, where it can be denser. Also, air becomes less dense with elevation, so that makes breathing more difficult at higher elevations. So sometimes, especially these people who climb the Himalayas or mountains that are really tall, have to carry their own oxygen or have a base camp where they can go down and get some breaths, and then they can start going back up again to prepare their bodies for that less dense air, because they're going to have to work harder at breathing. We take it for granted how easy it is to breathe as air rushes in. And like I was talking about, the atmosphere actually has layers. Yes, layers, and each of them has their own name and properties. The atmosphere is divided into 4 main layers based on the temperature changes that occur at different distances above Earth's atmosphere. And because of these temperature changes, you also have decrease and increase of densities. You've got different characteristics. So first, the troposphere, then the stratosphere, mesosphere, and thermosphere. So we'll take note on those as we go through them. You'll see here in this diagram that you have temperature and altitude, temperature going across the x-axis and altitude going on the y-axis. We also notice that across the top there's pressure. So I mentioned that pressure and temperature changes happen within these layers. So first you got this increase, as you're in the troposphere, you have this increasing temperature, and you have your pressure is decreasing as you're going up. And you can see then that on the red line marks the temperature and the green line marks that pressure. Then you start to have clouds forming and things like that. And then you hit another layer called the stratosphere. And then you start noticing a decrease in temperature. Why? Well, we'll get to that in the next couple of slides. So the troposphere is the lowest layer of the atmosphere in which temperature drops at a constant rate as altitude increases, hence the snow-capped mountains. This is part of the atmosphere where weather conditions exist. I would make a special note of that. The troposphere is Earth's densest atmospheric layer and extends 18 kilometers above Earth's surface. Now, let's make a note of stratosphere. So we're going to get back to why is the graph suddenly changed right there? This layer is the layer of the atmosphere that lies immediately above the troposphere and extends about 18 to 50 kilometers above the Earth's surface. Temperatures rise as altitude increases because, there it is, because ozone in the atmosphere absorbs the sun's ultraviolet energy and warms that air. So now you have all this ozone. So some people said, well, we could fix the hole in the ozone by just releasing more ozone into the atmosphere, and it'll close that hole up. Well, the problem is getting it up there and making it work the way that you want it to. We'll get back to the hole in the ozone here in a little bit. And then you had, so like I said, ozone, which is O3, 3 oxygen molecules combined. We breathe out O2, so it's not the same thing. Is a gas molecule that's made up of 3 oxygen atoms. Almost all of the ozone in the atmosphere is concentrated in the stratosphere, so you got to get it up there. Because ozone absorbs ultraviolet radiation, it reduces the amount of harmful UV radiation that reaches Earth. So it's important to close that hole up so that and allow that ozone to absorb the heat before it reaches the Earth. UV radiation that does reach Earth can damage living cells. So we have ozone to thank for it. So I said I was going to talk about this. There used to be a lot of hairspray cans and things like that that used different types of gases that would strip away the oxygen, one of the oxygen molecules from the ozone, and so it's no longer ozone, and cause this hole to happen. Now, since then, we've taking those things out of things like refrigerators and hairsprays, and it's starting to slowly close up. The mesosphere, the layer above the stratosphere, is the mesosphere. This layer extends at an altitude of above 80 kilometers. This is the coolest layer, not like cool, but the coldest layer of the atmosphere, where temperatures have been measured as low as negative 93 degrees Celsius. Well, you got a hot layer below it, so why is this layer cold? You gotta think what's happening to density. Thermosphere, the atmospheric layer located furthest from Earth's surface, is the thermosphere. Here, nitrogen and oxygen absorb solar radiation. So now you've got these other gases doing something similar to what the ozone was doing, resulting in temperatures measuring above 2000 degrees Celsius. Not only that, but it's more in direct line with the sun and its rays. The air in the atmosphere is so thin that air particles rarely collide, so the heat's not being transferred. You have to like literally run into them with your spaceship or whatever to be heated up by these, and would therefore it would not feel hot to us, just not if we're not bumping against them and getting that transfer of heat. The absorption of X-rays and gamma rays by nitrogen and oxygen causes atoms to become electrically charged in the thermosphere. So this is going to lead to things like the aurora borealis. Electrically charged atoms are called ions, and the lower the thermosphere is called the ionosphere. Ions are irradiated energy of light, and these lights often glow in spectacular colors in the night sky near Earth's north and south poles. So you got the So we're going to stop right here and pick up tomorrow on energy transfer and global warming and the 3 ways that energy is transferred. I want to end with this. I was talking about the aurora borealis. That would be the lights that you see in the north. The aurora australis is the lights that you would see in the South Pole. That one's not talked about as much because well, you don't have those land masses. You don't have as many people living down there as you do living up north. So be sure to get those notes. Check in tomorrow for part 2 and also the quiz. Sorry, I mean the lab. Be sure to email me and let me know if you need any thermometers. Thank you.